This is the third session on Newton's laws of motion. So in this video, I'll take up the theoretical discussion on Newton's third law. Previous video, I took up the theoretical discussion on Newton's first law in great detail. Second video was quite long video, but this will be a small video, okay? So I'll take up a theoretical discussion on Newton's third law. So Newton's third law, okay? Take a theoretical discussion on Newton's third law. So first of all, I'll state what is the statement of Newton's third law, okay? See, suppose we are given two material bodies, okay? Body B1, body B2. They are two material bodies. Now, these two bodies are said to interact with each other if they exert forces on each other. So we say that body B1 and body B2 interact with each other if they exert forces on each other. Okay? So बोलेंगे B1 and B2 are said to interact with each other if they exert forces on each other. If they exert forces on each other. If they exert forces on each other, then we say that bodies B1 and B2 are said to interact with each other. If they exert forces on each other, then these forces are termed as interaction forces. If B1 and B2 exert forces on each other, then the force which they exert on each other, they are termed as interaction forces. This force means interaction forces. I mean interaction forces. This is what the meaning of the word interaction forces. Okay. So if two bodies exert forces on each other, then these forces are called interaction forces. Now what is the statement on Newton's third law? Newton's third law states that interaction forces between pair of two material bodies B1 and B2 are equal in magnitude and opposite in direction. That is, interaction forces are equal and opposite. That is the exact statement of Newton's third law. That is the exact statement of Newton's third law. Interaction forces between two bodies are equal and opposite. That is, they are equal in magnitude and opposite in direction. This is the statement of Newton's third law. This is a famous version. Even in school days, you must be knowing it. Sometimes you say that to every action there is equal opposite reaction. There is also another way of saying the Newton's third law. So interaction forces between two bodies are equal in magnitude and opposite in direction. Interaction forces between the two bodies are equal in magnitude and opposite in direction. That is, interaction forces are equal and opposite. Interaction forces are equal and opposite. That is, interaction forces are equal and opposite. So this is the statement of Newton's third law, okay, famous version. Now I will take some examples, okay. So I'll take up some examples on Newton's third law, okay. Suppose a block lies on a smooth horizontal surface, say horizontal ground. Then this surface over which the block lies, this surface exerts normal force N on the block, which is right angle to the contact surface. And from Newton's third law, this block exerts equal opposite normal force on the surface, and these two are called the pair of interaction forces. They are the pair of normal forces between the body and the block and the surface in contact. All right, fine. Is it clear what I have said? So these are the pair of interaction forces between the block and the surface. They are equal in magnitude and opposite in direction. They are equal in magnitude and opposite in what direction? Fine. All right. So they are equal in magnitude and opposite in direction. So these are the pair of interaction normal forces between the two blocks, block and the surface. They are equal in magnitude, opposite in direction. Okay. I'll take up some more example. For example, suppose that there is a rough horizontal surface. A block is sliding towards rightward over a rough horizontal surface. This horizontal surface exerts a friction force F on the block opposite to the direction of relative slip. By Newton's third law, this block exerts an equal opposite friction force on the surface. So these are examples of interaction forces between the block and the rough horizontal surface. I'll take up some more examples. Suppose there is a string, a block is hanging from a string. This is the point where the block and the string are attached. This is the point where the block and the string are attached. This string exerts a force tension T on the block in upward direction. And by Newton's third law, this block exerts equal opposite force T in downward direction. This is an example. These are the pair of interaction forces between the block and the surface. Alright, fine. We can take some more examples. We can take, suppose some more examples. I'll take this. For example, suppose there is a container containing some liquid. A container containing some liquid. A block is inside this, solid body is inside the liquid. This liquid exerts a vertical contact force Fb on the submerged body, and this block exerts an equal opposite force Fb on the liquid in downward direction. These are the pair of interaction forces between the block and the liquid. They are the interaction forces between the block and the liquid. Okay. I'll take up some more examples. Okay, fine. Some example. For example, suppose two bodies are there. Body B1, body B2. They exert attractive gravitational forces on each other. According to the law of universal gravitation of Newton, Gm1 m2 by r square. So B1 and B2 exert equal opposite gravitational forces on each other, F. They are equal in magnitude, opposite in direction. These two F are also examples of interaction forces. Okay. These two forces are also example of what? Interaction forces. They are also examples of interaction forces. Okay. They are equal in magnitude and opposite in direction. Alright. They are equal in magnitude and opposite in what direction? This is also a pair of interaction forces between the two bodies. We'll take up some more example. Suppose we have 2 point charges Q1 and Q2. Suppose here they are both positive. From Coulomb's law, they repel each other with a force equal opposite force F K Q and Q2 by r square. You might be knowing in school days. Q1 and Q2 are 2 point charges separated by some distance r. Same sign I assume. Both I assume to be positive. Then Q1 and Q2 repel each other with equal opposite force F. So these two particles interact with each other and exert equal opposite Coulomb forces on each other. These pair of forces are called Coulomb forces or Coulomb repulsion between the two charges. Okay, fine. These are some examples of Newton's third law. One more point should be noted, should be kept in mind. See, for example, suppose it's like this. Suppose this is ground, okay, earth. a block is lying here. A block is lying here. Suppose say a block is lying here, say. Okay, fine. Now this is the center of Earth. Okay. So this block, this Earth attracts the block towards itself with some gravitational force Fg. By Newton's third law, this block exerts equal opposite force Fg on the Earth towards itself. So this Earth exerts an gravitational attraction force Fg on the block. And by Newton's third law, this block exerts a gravitational attraction force Fg on Earth in upward direction. They are the examples of action-reaction pair. See, these two pairs of interaction forces are called action-reaction pair. Okay. For example, these two forces are action-reaction pair. These two forces are also action-reaction pair. These two forces are action-reaction pair. These two forces are also action-reaction pair. These two forces are also action-reaction pair. These two forces are also action-reaction pair. So the pair of interaction forces between the two bodies, they are termed as action-reaction pair. Okay. So these are the action-reaction pair. One more thing. This Earth exerts a normal force N on the block in upward direction. And by Newton's third law, this block exerts equal opposite normal force in downward direction. So these two normal forces are also action-reaction pair. They are the pair of interaction forces between the block and the surface. They are equal in magnitude, opposite in direction. Okay. So these are all examples of action-reaction pairs. Okay. Or interaction forces which are equal in magnitude, opposite in direction. One more thing should be kept in mind. These action-reaction pair are not on the same bodies. They are on the different bodies in contact. That is what I would like to say is that these FB and FB, these two FBs, they are action-reaction pair, but they are not on the same body. This FB is on this due to liquid, and this FB is on liquid due to the block. So action-reaction pair are not on the same body, they are on different interacting bodies. Okay, so this point should be kept in mind. Action-reaction pair are not on the same bodies. Action-reaction pair are not on the same bodies. Okay, fine. So action-reaction pair are not on the same bodies. They are on the different bodies which interact with each other. Okay. This point also I have cleared. Okay. I'll rub this one. Okay. Now, one more thing you must note. See, there are two different versions of Newton's third law. Two versions of Newton's third law. First is the weak version, and second is strong version. Second is the strong version. Okay. First is the weak version, second is the strong version. What is this weak version? See, weak version states that interaction forces between two particles are equal in magnitude, opposite in direction, but they are not directed along the line joining the two particles. That is called the weak version of Newton's third law. Weak version of Newton's third law. What does it state? Interaction forces between two particles are equal in magnitude, opposite in direction, and they are not directed along the line joining the two particles. That is called the weak version of the Newton's third law. For example, I show it here. See, P1 and P2 are two particles. This is a line joining the two particles. Suppose P1 exerts a force F on P2. P2 exerts equal opposite force minus F on P1. So these two forces are equal in magnitude, opposite in direction, but these two forces are not along the line joining the two particles. This is called the weak version of Newton's third law. This is called the weak version of Newton's third law. Okay, so this is called the weak version of Newton's third law. Generally, weak version of Newton's third law is not encountered very frequently in everyday life, okay? But certain weak version of third law is found sometimes in the nuclear decay processes. Their weak version of third law is found to hold, okay? It's not very frequent, but. So what is the significance of the weak version of Newton's third law? Weak version of Newton's third law is a sufficient condition to prove the conservation principle of linear momentum of a collection of weakly interacting particles. What is the meaning of the word weakly interacting particles? Weakly interacting particle means particles exerting forces on each other as per the weak form of Newton's third law. So you must know the theoretical aspects of this third law. So weak version of Newton's third law is sufficient to prove the conservation principle of linear momentum of a collection of weakly interacting particles. Sufficient to prove the conservation principle of linear momentum of a collection of weakly interacting particles. Collection of weakly interacting what? Particles. So this is the weak version which I have said, okay? Now what about the strong version of Newton's third law? What does strong version state? See, strong version says that interaction forces between two particles are equal in magnitude, opposite in direction, and they are directed along the line joining the two particles. That is called the strong version of Newton's third law. Various examples are found in everyday life in Newton's third law. For example, say, consider 2 point charges Q1 and Q2, say of same sign. Suppose say both are plus. From Coulomb's law, Q1 repels Q2 with a force F in that way, and by Newton's third law, Q2 repels Q1 with equal opposite force in backward direction. So these two interaction forces are equal in magnitude, opposite in direction, and they are directed along the line joining the two particles. So this is an example of a strong version of Newton's third law. I'll take up some more example. Imagine we have 2 point charges plus Q1 and minus Q2. Now they have opposite signs, so they will attract each other as per the Coulomb's law. Q1 will attract minus Q2 towards itself with a force F, and minus Q2 will attract Q1 with equal opposite force F. So these two interaction forces are equal in magnitude, opposite in direction, and they are directed along the line joining the two particles. This is also an example of a strong version of Newton's third law. Fine. I'll wrap this one, okay? Now I'll take up some more examples on strong version. Suppose we are given two particles of masses m1 and m2. They are separated by a distance r. Now they will attract each other as per the Newton's gravitational law gm1 m2 by r square. So they exert equal opposite gravitational forces on each other, G for gravitational. These two forces are equal in magnitude, opposite in direction, and they are directed along the line joining the two particles. This is also an example of strong version of Newton's third law. This is also an example of strong version of Newton's third law. Alright, fine. Now what is the significance of the strong version of Newton's third law? Strong version of Newton's third law is sufficient to prove the conservation principle of angular momentum of a collection of strongly interacting particles. What does the word strongly interacting particle mean? A pair of particles exerting forces on each other as per the strong version of Newton's third law. As per the strong version of Newton's third law. That is called the strong version of Newton's third law. So, strong version is sufficient to prove. Strong version of Newton's third law is sufficient to prove the conservation principle of angular momentum of a collection of strongly interacting particles okay, this is called the strong version of Newton's third law. So you must know these physical significance of these two laws. So they have their own importance. These points should be clear in mind. It's a concept building phase now. Okay. So strong version of Newton's third law is sufficient to prove the conservation principle of angular momentum of a collection of strongly interacting particles. What does the word strongly interacting particle mean? Particles exerting forces on each other as per the strong version of Newton's third law. Fine. So in this third video on Newton's laws, I fully discussed the third law of Newton and both its versions and some examples. Okay. So I'll close it here. In next video, I'll take up the Newton's second law detailed discussion then, and then I'll pass over to numericals of all types. Okay. So this I close it here. Fine. All right.